student-master for a basic understanding of biochemistry, as well as many other areas, involves changes occurring during acid-base transitions. I believe the simplest way to develop the concepts involved is to start by discussing water. You all know that water is written as H2O. Undoubtedly, you're also aware that water can be dissociated into hydrogens called protons and hydroxyl ions. Therefore, it's possible to write the equation for the dissociation of water into protons and hydroxyl ions as shown on the first slide. Note that the reaction is written on this slide as expressed with arrows in both directions. That is, water can be dissociated into hydrogen ions and hydroxyl ions, and there can be an association of hydroxyl ions plus hydrogen ions to give water. What else is obvious? You can immediately see from the equation that for every hydrogen ion formed, there is a hydroxyl ion formed. The extent of dissociation of water is very small. That is, the amount of undissociated water is very large. Another way of expressing this is to state that the volume of the reaction, as shown on the is largely to the left-hand side of the reaction. One can write an equation expressing the dissociation of water as shown on the first slide. K, a constant, is equal to the concentration of hydrogen ions times the concentration of hydroxyl ions divided by the concentration of water. The dissociation constant K is an expression of the extent of dissociation of hydrogen and hydroxyl ions from water. Brackets in the equation represent concentrations. Now, if we take the top portion of the equation, we can rewrite the expression for what's called the ion product, shown on slide 1. K sub W, the ion product of water, is equal to the concentration of hydrogen ions times the concentration of the hydroxyl ions. It's been determined from a number of physical methods that at 25 degrees, the ion product of water equals 10 to the minus 14. That means there are 10 to the minus 7 hydrogen ions, 10 to the minus 7 hydroxyl ions in 1 of pure water. Now, if we're to relate the ion product of water to the equation shown in the first part of the first slide for the dissociation of constant of water, we can calculate that the dissociation constant for water is about 1 point times 10 to the minus 16. All right? Sit and think about that for a while. Do you know how I got that number? If you want to know how the ion product of water was determined, I suggest you read a textbook of physical chemistry for your own information. In the link above, I'll give you the hint that the concentration of water is 55.5 molar. As stated in your textbook, Principles of Biochemistry by Whitehandler and Smith, the ion product of water is of fundamental importance in considering the behavior of acids and bases in solution. Alteration in hydrogen ion or hydroxyl ion concentration must always result in an immediate compensatory change in the concentration of the other ions. Let's say that again. K sub W is a constant. If you change the concentration of hydrogen ions, there must be likewise a change in the inverse direction of the concentration of hydroxyl ions. For example, if the concentration of hydrogen ion is 10 to the minus 5, then the concentration of the hydroxyl ion must be 10 to the minus 9, so that the product of the two is equal to 10 to the minus 14. Instead of dealing with exponential functions all the time, the biochemist uses the negative of the concentration of hydrogen ions or hydroxyl ions. This is a concept which was first introduced by a Swedish scientist named Sorensen, S-O-R-E-N-S-O-N. As shown in slide 2, the negative logarithm of the hydrogen ion concentration is defined as pH. That's small p, capital H. You must remember that in this instance, logarithms used are to the base 10 and are not natural logarithms. Therefore, if you have a solution with a hydrogen ion concentration of 10 to the minus 5, then pH is 5. What if the concentration of hydrogen ion were 0.1? What is the pH of the solution? Well, the negative log of 10 to the minus 1 is 1. So pH, therefore, is 1. Let's try another problem to reinforce the basic principles involved in doing logarithms. Suppose you had a solution of pH 7.3. What is the concentration of hydrogen ions present? First, you would set up an equation as shown in slide 2, where pH is equal to the negative log of the hydrogen ion concentration. The pH is 7.3, so you therefore must determine what is the negative log of 7.3. Another way of expressing this is that the logarithm of the hydrogen ion concentration equals minus 7.3, or minus 8 plus 0.7. The anti-logarithm of minus 8 is 10 to the minus 8. The anti-logarithm of 0.5. Therefore, in our little problem, ion concentration at pH 7.3 is 5 times 10 to the minus 8. What then is the hydroxyl ion concentration? Sit down and calculate this. You will also note that on your worksheets we provide you with copies of logarithm tables so that you don't have to look these up. Why don't you stop at this point, turn off your recorder, and do a few of the simple problems that we have included on your worksheets. All right, now having done those problems, let's hope that by working the problems that you now have some understanding of hydrogen ions and pH, and in particular, logarithms. It's directly comparable to discuss hydroxyl ions and pOH, although this is rarely used in biochemistry. Repeat the principles again for you. The negative logarithm of the hydrogen ion concentration equals pH. In a comparable manner, the negative logarithm of the hydroxyl ion concentration is expressed as pOH. In the same way, the biochemist expresses the negative logarithm of the ion product constant K sub W for water as pKW. Therefore, in what you have learned so far, you can see that pKW equals pH plus pOH, or at neutrality, 14 equals 7 plus 7. Pure water, which on dissociation, as we've shown, should have equivalent amounts of hydroxyl and hydrogen ions, should be at pH 7. In practical terms, this rarely occurs because pure water always contains some contaminants. In general, carbon dioxide is absorbed from the atmosphere. Let's hope, however, that you do understand that at neutrality, there is an equivalent concentration of hydrogen ions and hydroxyl ions. That is, the solution is at pH 7. Also, you should be aware that hydrogen ions do not exist as such, but are present in the hydrid form as H3O+. This is called a hydronium ion. For simplicity's sake, however, we generally do not write protons or hydrogen ions in this form. However, this should not change our understanding that in reality, when we speak of hydrogen ions, we mean the hydronium ion. If you want to find more about how the pH scale is calibrated, in particular the use of the hydrogen electrode as a standard, I would suggest that you consult a book of physical chemistry. Having understood now something about water and its dissociation, as well as relationship to pH, let's next turn our attention to a discussion of acids and bases. The easiest situation to consider is how to handle strong acids. Strong acid, by definition, is considered to be completely dissociated in water. Therefore, if you place hydrochloric acid in water, it completely dissociates into hydrogen ions and chloride ions. There is no reservoir of undissociated hydrochloric acid. How does it affect the pH of the solution? The best way to determine this is by looking at a few problems. Before doing such problems, however, on the effect of strong acids on pH, we must review a few basic principles concerning the expression of hydrogen ion concentration. You will recall from your general chemistry that an acid such as hydrochloric acid dissociates to form one hydrogen ion and one chloride ion. Therefore, a 1 molar solution of hydrochloric acid, if we have this solution, is 1 normal and contains 1 equivalent of hydrogen ion. If we had 1 liter of a 1 molar solution of sulfuric acid, H2SO4, we would have a 2 normal solution of sulfuric acid, or equivalents of hydrogen ion. Likewise, with phosphoric acid, H3PO4, we would have in a 1 molar solution a 3 normal concentration, 3 equivalents of hydrogen ions. Equivalents are an expression of the hydrogen ion concentration times the liters of solution employed. Let's try and reinforce that concept. If you had 10 liters of a 1 normal solution of hydrochloric acid, 10 equivalents of hydrogen ion. If you had 100 milliliters of a 1 normal solution of hydrochloric acid, you would have 0.1 equivalents, or 100 milliequivalents. Let's see if you really understand that point by working out a simple problem. Suppose you owned a goldfish bowl of unknown volume but large enough so you didn't want to dump it all out to find out how many liters it contained. How would you go about determining the volume of water in this goldfish bowl? The simplest way to approach this problem is to fill the goldfish bowl with water and add 10 milliliters of a 1 normal solution of hydrochloric acid. This is the same as adding 10 milliequivalents of hydrogen ion. Now you mix it all up and you withdraw a 10 milliliter sample of the diluted acid and titrate this sample with a standard solution of 0.01 normal sodium hydroxide. When you do this, you find it requires 20 milliliters of the sodium hydroxide to neutralize the acid in the 10 milliliter sample you took out of the goldfish bowl. You sit down and do some simple calculations, and you find that the volume of the goldfish bowl is 500 milliliters. How do you do this? Well, work it out on your worksheet. You'll see that 20 milliliters of a 0.01 normal sodium hydroxide solution would neutralize 0.2 milliequivalents of acid. You have 0.2 milliequivalents of acid in 10 liter sample. To account for the 10 milliequivalents of acid originally, you would have had to dilute the hydrochloric acid to a volume of 500 ml. Of course, this didn't get very far because you had to empty the goldfish bowl now. But let's pose a nice simple problem to explain to you one way of handling molarity and milliequivalents. Now, stop the recorder and work out some of the problems on your worksheet. Now let's return to our question on the handling of pH for strong acids. Let's assume you prepared a 0.1 normal solution of hydrochloric acid. As we said above, this means that under ideal conditions, the hydrochloric acid will completely dissociate, and you will have 0.1 moles per liter of hydrogen ion and 0.1 moles per liter of chloride ion. The negative log of 0.1 is 1, so the pH, therefore, of a 0.1 normal solution of hydrochloric acid is 1. As you may know, this is not absolutely correct, since we cannot talk of molarity of hydrogen ions and must consider instead the activities of the hydrogen ions. For simplicity's sake, however, the biochemist equates concentration with activity of hydrogen ions. But it is with the realization that this can only be done with rather dilute solutions and not with concentrated solutions. To explain what is the difference between concentration and activity in the sense that we are employing it here would require a much more complete understanding of the physical-chemical application of the hydrogen electrode, and it's beyond the scope of our present discussion, so don't worry about it. Suffice it to say that for our purposes we will equate activity and concentration if we realize that we are not absolutely correct when discussing concentrated acids. Let's return to our example. For a 0.1 normal solution of hydrochloric acid, the pH is about 1. The hydrogen ion concentration is 0.1 moles per liter. What is the pOH? As described above, pOH plus pH must equal pKW. If the pH is 1, then the pH must be 13 to equal a pKW of 14. Try calculating the pH of a 10 to the minus 3 normal solution of hydrochloric acid. Do the same on your worksheets for a 10 to the minus 2 molar solution of sulfuric acid. Remember, sulfuric acid is H2SO4. I hope that you found out that a 10 to the minus molar solution of sulfuric acid has a pH of about 1.7. Before going on to the case of weak acids, let's discuss a few more points on strong acids. You already gathered that when base is added to an acid, a change in pH occurs. Now we can express the change in pH by plotting the amount of base, such as sodium hydroxide, added to a known solution of acid, such as hydrochloric acid, as a function of pH. This is shown on slide 3. In this case, we've taken 10 milliliters of a 0.1 normal solution of hydrochloric acid and titrated this with varying amounts of a 0.1 normal base sodium hydroxide. You already calculated what the hydrogen ion concentration is in the acid solution before any base is added. Now, if we add 1 milliliter of the base to 10 milliliters of the acid, this base will neutralize an equivalent amount of the acid and increase the volume to 11 milliliters. If the volume remained the same, the normality of the acid remaining would be 0.9. But as the volume has increased from 10 to 11 milliliters, the normality is approximately 0.082, which is also the concentration of the hydrogen ions. The pH, as you can calculate, is 1.09. Therefore, you can see that in neutralizing 10% of the hydrogen ions, the change in the pH is very little. Now, to go from pH 1 to 2, it would be necessary to reduce the hydrogen ion concentration to 1/10 the original concentration, or to give 90% neutralization of the total acid present, neglecting any effective dilution. Likewise, in order to go from pH 2 to pH 3, it would be necessary to again neutralize 9/10 of the remaining hydrogen ions. But the total number of hydrogen ions to be neutralized now, in this case at pH 2, is only 1/10 that present at pH 1. Therefore, it would take only 1/10 as much base, or approximately 0.9 milliliters, to change the pH from 2 to 3. You can do a similar calculation when going from pH 3 to 4 and so forth. Thus, you can see that there is a very rapid increase in pH that occurs after adding a fixed amount of base to the solution. Now, there are a number of ways in which one can determine the change in pH. You can either do calculations of the type that we've described, or in more practical terms, you can use a pH meter in the laboratory. A pH meter consists of a glass electrode which has a special glass membrane permeable to hydrogen ions, and a reference electrode, such as a calomel electrode, whereby you can establish an electromotive potential. And you measure this potential and relate it directly to the pH of the solution. I hope that as the course goes by, the opportunity will arise during your visits to a laboratory or during one of the discussion periods for you to go into greater detail concerning a pH meter and its operation. Now, at this point, why don't you stop and take a breather? Let us continue our discussion of acid-base and extend the discussion to more practical problems. That is the case of weak acids. As you can imagine, it's rather rare in life that the biochemist working with biological solutions would encounter systems containing strong acids or bases, unless he was specifically doing titrations in the laboratory. It's far more common to work with weak acids or weak bases. What do we mean by weak? In general terms, this means that a chemical, when placed in water, is only partially dissociated. As shown on slide 4, the weak acid HA dissociates reversibly in water to produce hydrogen ions and A- ions. when one applies the mass law equation, you can express the equilibrium for this reaction with the equation shown on slide 4. That is, Ka, the equilibrium constant, is equal to the concentration of the hydrogen ions times the concentration of the anion A- divided by the concentration of the undissociated acid. The term Ka is called an ionization or dissociation constant for the acid. The bigger the value of Ka, the more acid is dissociated to hydrogen ions and anions A-. You'll recall that in the case of the strong acid hydrochloric acid, Ka would be 1. In the same way, one can speak of the dissociation of a base BOH. BOH can dissociate into positive B+ ions and hydroxyl ions, and one can likewise determine a base dissociation or ionization constant called K sub B. If we stick to the case of the weak acid and try to explain that instance first, then you can work out the case for the weak basis for yourself. Let's look at the equation for the dissociation of a weak acid as shown in slide 4. The equation Ka equals the concentration of the hydrogen ions times the concentration of the anion A- divided by the concentration of the undissociated acid. This equation can be simply rearranged so that we can express the concentration of hydrogen ions as equal to the product of K sub A times the undissociated acid concentration divided by the concentration of the anion A-. Now, if we take the logarithm of both sides of this equation, you find, as shown on slide 4, that the logarithm of the hydrogen ion concentration equals the logarithm of K sub A plus the logarithm of the concentration of the undissociated acid minus the logarithm of the concentration of the anion A-. If we now multiply this equation by -1 to convert everything into negative logarithms, we get minus logarithm of the hydrogen ion concentration equals minus the logarithm of the dissociation constant of the acid, Ka, minus the logarithm of the undissociated acid, Ha, plus the logarithm of the anion A-. We told you before that the negative logarithm of the hydrogen ion concentration is pH. In the same way, the negative logarithm of the acid dissociation constant Ka is called pKa. So you can therefore rewrite the equation in a term more familiar to biochemists. pH equals pKa plus the logarithm of the concentration of the anion A- divided by the concentration of the undissociated acid. I didn't really pull a fast one on you. If you remember the fundamentals of logarithms, you'll see that the log of A- over HA is the same as minus the log of HA plus the logarithm of A-. The general form of this equation is shown on slide 5. pH equals pKa plus the log of the concentration of the salt over the concentration of the acid. This is a fundamental equation that you must know. It's called the Henderson-Hasselbalch equation. How do we apply this equation, and what is its practical usefulness? Biological systems, that is cells, are composed of many weak electrolytes. That is compounds that do not completely dissociate in water. These compounds exert a buffer action which is of primary importance in maintaining the narrow pH limits required for survival of a cell. Let's try some simple calculations using acetic acid as an example. Acetic acid is a carboxylic acid with structures shown in slide 6, and it can dissociate into hydrogen ions and acetate ions. The dissociation constant for this reaction is about 2 times 10 to the minus 5. What is the negative logarithm of 2 times 10 to the minus 5? Well, it's about 4.7. So the pKa, that is the negative logarithm of the dissociation constant, is 4.7. What then is the pH of a 1 molar solution of acetic acid? If we set up our equation as shown earlier and repeated now on the slide in front of you, so that Ka equals the concentration of the hydrogen ion times the concentration of the acetate ion divided by the concentration of undissociated acetic acid, we see that 2 times 10 to the minus 5 equals the concentration of the hydrogen ion times the concentration of the acetate ion divided by 1. Or the concentration of the hydrogen ion is about 4.4 times 10 to the minus 3. And the concentration of the acetate ion is the same. That is 4.4 times 10 to the minus 3. The negative logarithm of 4.4 times 10 to the minus 3 is about 2.4. So the pH of a 1 molar solution of acetic acid is about 2.4. Now you'll notice that in our calculation we used 1 as the concentration for the undissociated acid. You realize now that even if we did subtract the 4.4 times 10 to the minus 3, which is the amount of acid which has dissociated, it would have little or no influence on the concentration of the undissociated acid. Now, if we titrate the acetic acid solution with an alkaline solution of sodium hydroxide so that we neutralize half of the acid present, that is, we added, say, a half a milliliter of a 1 normal solution of sodium hydroxide, or 0.5 milliequivalents, to 1 milliliter of a 1 molar solution of acetic acid, that is 1 milliequivalent, we would find that the concentration of the undissociated acetic acid and sodium acetate present were equivalent. Now let's try and calculate the pH of the solution using the Henderson-Hasselbalch equation. First, let's write the equation for what's occurred. This is shown in slide 7. We've already discussed that acetic acid is a weak acid, so it is only partially and poorly dissociated into hydrogen ions and acetate ions. Sodium hydroxide is a strong base, so it is completely dissociated into sodium ions and hydroxyl ions. There is a partial neutralization of the hydrogen ions that occur to form water, and likewise the formation of the sodium salt of acetic acid or sodium acetate. Salts in general are considered as completely dissociated, so these are present as sodium ions and acetate ions. We started with a 1 molar solution of acetic acid, and we have converted 1/2 of this to sodium acetate. So we end up with only 0.5 milliequivalents of acetic acid and 0.5 milliequivalents of the sodium salt, sodium acetate. If we return to our Henderson-Hasselbalch equation, where pH equals pK plus the log of the concentration of the salt over the concentration of undissociated acid, and we stated above that the pKa for acetic acid is 4.7, then the concentration of salt in our case is 0.5, and the concentration of the remaining free acid is also 0.5. The log of 0.5 over 0.5 is 0. So the pH equals the pK, or pH equals 4.7. This is an important principle that must be remembered. With a weak acid or base, when it is half neutralized, the pH equals the pK. You're probably asking yourself at this point, what does this have to do with buffers, and what's so wonderful about all of this? If we were to add, in our example, 0.1 milliliter more of our 1 molar solution of sodium hydroxide, that is 0.1 milliequivalents, we now have 60% of the acid converted to the salt and 40% of the free acid remaining. Again, using the Henderson-Hasselbalch equation, we see that pH equals 4.7 plus the log of 0.6 over 0.4, the concentration of undissociated acid, or the pH equals 4.87. Therefore, by neutralizing 10% more acid, it caused a very minimal change in pH. That is, about 0.17 pH units. It's important to compare these results with the same type of behavior observed with strong acids such as hydrochloric acid. You'll remember that earlier we described for you that at pH 5, the concentration of hydrogen ions and hydrochloric acid was 0.00001. I hope I got that right. If we were to add 0.1 milliequivalents of our sodium hydroxide to such a solution, then the pH of our strong acid would be changed greater than pH 13, since there is no reservoir of undissociated acid to buffer the effect of adding the base. This can be more dramatically shown to you by looking at the data presented in slide 8. Here we show the effect of titrating 10 milliliters of a 10th molar solution of hydrochloric acid or acetic acid with 0.1 solution of sodium hydroxide. You can see, as we discussed earlier, that in the titration of hydrochloric acid, there is a considerable amount of alkali required until about pH 2 is obtained. And only a very small amount of alkali will make a rapid change in pH from 2 to about 11 or 12. In the case of acetic acid, we start originally at about pH 2.5. As more alkali is added, a gradual change in pH occurs until we reach about pH 6, after which point there is then a change in the pH of the solution. And the curve becomes similar to that shown for hydrochloric acid. Therefore, if you wanted to maintain a solution with about pH 5, you would not select hydrochloric acid to use to keep the system at this pH, since it would require very little alkali to cause a dramatic change in the pH. If you were to use acetic acid, however, you would see that you can absorb considerable number of neutralizing equivalents without markedly changing the pH of the solution. This concept of buffering is very important, biochemically, both in the sense of those organisms that must maintain reasonably constant values of pH in the intracellular fluid, and in the sense that proper handling of biochemical materials in the laboratory requires the maintenance of a constant pH. The buffer capacity of the system is maximal at a value of pH equal to the pK of the acid component of the buffering system. This is important to remember. A general rule of thumb is the following. A buffer may be effectively used plus and minus 1 pH units from the pK value. Let's state that a little differently. If one has acetic acid with a pKa value of 4.7, this acid would demonstrate its best buffer capabilities between pH 3.7 and 5.7. Now, there are a number of assumptions incorporated in the Henderson-Hasselbalch equation, which limit its usefulness at the extreme ends of the titration curve. In general, it's applicable between 10 and 90% neutralization of an acid or a base. Well, so far, we've described the situation for handling the weak acid, acetic acid, and the associated titration curve for this weak acid. Now, included on your worksheets for your information, a table for the various values for pKa for the dissociation of some of the important acids encountered in biological systems. You'll note that these range from pK values of about 1 all the way up to 11 or 12. Now, I'd like you to stop at this point, shut off the recorder, and work out a number of problems using the data for the pKa values and the Henderson-Hasselbalch equation to solve these problems. Are you ready to make another stab at it and see how much further we can go? Now, one of the more complicated systems to be considered, and one which would be instructive for you and also of great biological importance, is the case of the changes associated with the titration of phosphoric acid. You recall that we described earlier that phosphoric acid has 3 hydrogen ions which can be dissociated. These hydrogen ions, however, do not all dissociate at one time, and there's a series of reactions which occur during neutralization. These reactions are shown in slide 9. Phosphoric acid starts out as H3PO4, and it's initially neutralized with hydrogen phosphate anion plus hydrogen ions. This has an extremely low pK and acts in many respects like a strong acid. Further neutralization results in the conversion of the dihydrogen phosphate anion to the monohydrogen phosphate anion, PO4 minus together with a hydrogen ion. The pKa for this second dissociation is 7.2 and therefore is of great biological significance. Likewise, there's a third dissociation which can occur in the further neutralization of the HPO4 form. This is the conversion to the trivalent phosphate anion, PO4 Let's consider the changes in pH during the titration of a solution of phosphoric acid. This is shown on your next slide. By plotting the milliliters of a 0.1 normal solution of sodium hydroxide required to neutralize a 0.1 molar solution of phosphoric acid, and remember now that a 0.1 molar solution of phosphoric acid is the same as a 0.3 normal solution of phosphoric acid. Now when we plot the pH during the titration, we see that there are three distinct areas where there are marked changes in pH. Neutralization of the first hydrogen ion during titration with sodium hydroxide causes a gradual change in the pH from about 1.4 to about pH 3, at which point very little alkali will then cause a dramatic change of the pH to about 5.5. Again, the amount of sodium hydroxide required to cause a change of pH is considerable, and there is only a gradual change in pH associated with increasing amounts of sodium hydroxide until pH 8.5 is reached. Here, we've neutralized the dihydrogen phosphate form and converted it to the monohydrogen phosphate ion form. As can be seen, there is likewise a neutralization of the third hydrogen released. Thus, there is a stepwise function which occurs. To test whether you really understand the Henderson-Hasselbalch equation, we ought to consider a problem to try and establish what are the ionic species present at any given pH. At pH 7, in a mixture of phosphate salts, there are two forms which are present. Now there are some simple rules which can be derived from the data shown on the preceding slide. That's slide 9, which we considered earlier. Initially, we started out with undissociated phosphoric acid. The first stage in neutralization results in the formation of water plus the monosodium salt of dihydrogen phosphate. The second step of neutralization involves the conversion of the monosodium dihydrogen phosphate to the disodium monohydrogen phosphate form. This is the conversion which has a pK value of about 7.2. Now, if we asked you the question, what is the nature of the ionic species at pH 7.2, it'd be very simple. At that pH, the P would equal to pK, and the ratio of salt to acid, as derived from the Henderson-Hasselbalch equation, would indicate that there would be equal concentrations of disodium monohydrogen phosphate and monosodium dihydrogen phosphate. As we progress to the more acid part of the curve, we would, of course, increase the concentration of the sodium dihydrogen phosphate species relative to the concentration of the disodium hydrogen phosphate species. In this case, the dihydrogen phosphate species is considered the acid, whereas the monohydrogen phosphate species is considered the salt. To solve the question of what are the ratios of the ionic species present at pH 7.0, one would set up the Henderson-Hasselbalch equation where pH equals pK plus the log of the concentration of salt over concentration of acid. Now, we've told you that the pH is 7.0. The pK is 7.2. Therefore, we must determine that the log of salt acid equals minus 0.2. We can convert this so that the log of acid over salt equals 0.2. Now, this is a very simple trick which is legitimate using logarithms. That is to invert. What is the analog of 0.2? Well, you go to your logarithm tables and you find that the analog of 0.2 is 1.6. So the ratio of the acid form of phosphate to the salt form of phosphate at pH 7.0 is 1.6. Or expressed in a different way, for every 16 parts of monosodium dihydrogen phosphate species present, there are, at pH 7.0, 10 parts of the disodium monohydrogen phosphate species. Now see if you can calculate what it would be at pH 7.3. How much free phosphoric acid is there going to be in the solution at pH 7.3? The answer is very, very little. In fact, so little it is negligible and cannot be considered in our calculation. In the same way, we would consider there to be essentially no trisodium phosphate species present in the reaction mixture. Now, to better understand the utilization of the Henderson-Hasselbalch equation, in particular to those acids which have more than one dissociable hydrogen ion, it's best to carry out a number of independent calculations on your own. So before you do that, I would like to direct your attention to the examination of another acid, carbonic acid, and in particular the effect of bicarbonate ion. Now, one of the most important constituents of blood plasma is sodium bicarbonate. This is the so-called alkaline reserve which can react rapidly with metabolic acid. The ionization of carbonic acid, H2CO3, into hydrogen ion and the bicarbonate anion is shown on the next slide. Now, this reaction is reversible. It can be readily driven to the left-hand side by increases in concentration of hydrogen or by bicarbonate ions, or it can be driven to the right by the removal of either of these ions. The equilibrium for such a reaction is also shown on this slide, where K equals the concentration of hydrogen ion times the concentration of bicarbonate ion over the concentration of undissociated ion. Now, this acid, carbonic acid, has the potentiality of releasing two hydrogen ions during neutralization. The pK values for the two neutralizations are 6.3 and 10.2. The system is very similar to that which we have described for phosphoric acid, except in this case, there are 2 steps rather than 3 steps during the neutralization. Now, why don't you calculate what the pH of the solution would be if it consisted of 10 parts of bicarbonate ion, 1 part carbonic acid. Also, we'd like you to stop the recorder and calculate a number of problems which are included on your worksheet. Now that you've completed the calculation for those at more than one dissociable hydrogen ion, we'd like to turn your attention to consider the titration of acids such as, for instance, titrate with an acid of reactive groups present in amino acids, carboxyl group and the other amino group. This is which will be discussed in a subsequent tape. Again, the same rules apply. We finish this tape, try and rise the point that we've attempted to distribute. Now, very back early in the beginning, you were introduced to the concept of hydrogen and pH. You've also been introduced to treatment of strong acids and weak acids in regard to dissociation and their influence on the pH. This, of course, brought up the question of what is a buffer, and how do buffers have usefulness in biological systems. In addition, we have for you the Henderson-Hasselbalch equation. It has been described to you together with a number of equations. It is most important that you learn to master the use of the Henderson-Hasselbalch equation, that you have a clear understanding of pH as well as pK. Just to see whether you really do, if you're not completely exhausted at this point, why don't you work out some more problems that have been included on your worksheet. Now, if you have questions, problems, you have to discuss them with your instructors during the discussion. I also realize that although this has been an introduction into some of the basic principles of acid base, that you expected as your initiative the various books to read on acid base and other means of expressing or teaching the concept of acid base. Since what I've told you here is but one opinion on how to deal with topic thought. It's a rather complicated topic. Students generally have trouble. In particular, it is sometime going through a book, Acid Base by Christensen, and work out many of the problems that are described in that book. With what you've now learned off this tape, that book should be very simple to go through. In addition, we would hope that you would read your textbook. and get a different viewpoint in the understanding of acid-base and its application to biological systems. Now, I hope that this tape has been of some use to you. Don't forget down your comments so that it'll help when it is drawn up the next time.